Good morning, I'm Manuel Zarzo, and in this Unit 6 about inference of one normal population, I will explain errors in hypothesis tests. When we carry out or when we conduct a hypothesis test, there are two possible erroneous decisions that can be made. For example, imagine that make a test of COVID, okay? There are two errors. The test is positive, but the patient is not infected, or another different error is that the test is negative but the patient is really infected. Another example can be a court or a trial or a judgment, some judge that has to decide about if a person is guilty or innocent. Then again, there are two mistakes. The accused person is innocent but is declared guilty, or the accused is guilty but is declared innocent. Or for example, another case could be like an archaeological study. There are again two errors. The artwork can be fake but it is considered authentic, or the artwork is authentic but it is considered fake. So like this kind of things that I'm going to explain here in this subject of statistics can be applied also to many contexts of real life. So when we conduct a hypothesis test, there are two types of possible erroneous decisions that can be made. So they have a special name. It is called a type 2 error. By definition, it is to reject the null hypothesis when it is true. It's called also error of the first kind, alpha error, or false positive. Okay, and the other type of error is called type 2. It is to do not reject, which would be like equivalent to accept, although I explained in the previous slide that we prefer not to say accept the null hypothesis because it seems that we are demonstrating mathematically that the population average is a value or the population variance is a specific value. And then, as it is not exactly true, instead of accepting, it's better to say do not reject the null hypothesis when it is false than in the case that being true the alternative hypothesis. Well, it has other names like error of the first kind or beta error or false negative. Well, other important definitions are the following. Type 1 risk. The risk is the probability to make an error. Okay, so if the error of the first is type 2, we call type 1 risk the probability to make a type 1 error. This is called alpha, and this definition is very important in statistics because the value alpha will appear a lot of times in inference. And then it's also called significance level of the test. Very important. You have to remember that significance level is the same as type 1 risk. Most frequent values that we use in statistics is alpha 5% or alpha 1%. Then we have the type 2 risk, which is called beta. It is the probability to make a type 2 error. Then the complementaries of these probabilities have a special name. 1 minus alpha is called confidence level, and 1 minus beta is called power of the test. Okay? And then we have also another definition, a p-value. The p-value is very important, especially if we use a statistical software, because nearly all statistical softwares in statistics that are used for inference, they provide this p-value, which is also called sometimes the observed significance level. By definition, it is the probability of obtaining test results as least as extreme as the result actually observed, assuming that the null hypothesis is true. Well, actually, this definition is a bit abstract, a bit difficult to understand, but don't worry, I will explain that definition step by step with examples in another video. Well, this slide is very important because it contains a very important definitions. Some of them are not contained in the math tables that you can use for the exams or for the class exercises. So it is important that you try to remember. Okay, so the definition of alpha, the probability to make a type 1 error, which means the probability to reject the null hypothesis when it is true. It's a very important definition, very important. Or beta, the same. Beta, probability to make a type 2 error, which implies to do not reject the null hypothesis when it is false. So these are like the most important definitions that you should remember, you should learn. So then an exercise. Okay, so let's apply these new concepts in this exercise. Imagine that we have a random variable x as the number of defects in one piece, and then we count, so it's a discrete variable. There's like no maximum. We can have a piece or an item with a lot of defects, so we can fit that according to a Poisson distribution with a variable lambda. Okay, lambda is the average number of defects in one element. Okay, then we want to test the null hypothesis that the average number of defects per piece is lambda. Lambda is 2. Okay, so the null hypothesis is lambda equal 2 versus the alternative that lambda is bigger than 2. It means that it's a composite test. A sample of 10 pieces is taken, and then the average number of defects in this sample is computed. If this sample mean is bigger than 2.5, then the null hypothesis is rejected. Then, what is the type 1 risk alpha of this test? Well, to make this kind of calculation, you should remember the definition. And then if you go to your math tables, that definition is not inside that table. Well, so this is what you have to remember. Alpha, by definition, is the probability to reject the null hypothesis when it is true. So in this case, we are saying that if the sample mean is bigger than 2.5, the null hypothesis is rejected. So reject will be when the sample mean is bigger than 2.5. Considering that the null hypothesis is true, then considering that we are in a Poisson with lambda equal 2. Well, good. So what is the sample average? The sample average is when we sum these 10 random variables divided by 10. Okay. Then in this case, we can pass this value 10 at the other side of the inequality multiplying, which means that the probability of the sum of this Poisson distribution is bigger than 25. Then remember that we have the property that the sum of Poisson variables is also a Poisson distribution, with the lambda being the sum of the lambdas. So we sum 2 plus 2 plus 2 10 times, which implies a lambda of 20. So this is the probability that a Poisson distribution with lambda 20 is bigger than 25. Okay, so we can make the complementary so that we can use the ABAC of Poisson. We have to cut in the curve 25, so using the ABAC, the solution will be approximately 11%. Good. Then let's continue with the exercise. What is the type 2 risk beta of the test when lambda is equal to 4? Okay, so by definition, remember, beta is the probability of not reject the null hypothesis when it is false. Well, in this case, the null hypothesis is false because we're saying that lambda is 4. Good. In this case, not reject means that the sample mean is lower or equal to 2.5. Okay. So again, we make the same. The probability that this average is less or equal to 2.5. Again, we take the denominator, value 10, goes multiplying at the other side of the inequality. And then again, we have a sum of Poisson variables, which is another Poisson variable, with the lambda being the sum of the lambdas. Sorry. In this case, we're saying that lambda is 4. So we sum 4 plus 4 plus 4 10 times, which is the probability of Poisson distribution with lambda 40. In this case, we cannot use the ABAC of Poisson, which is until lambda equals 30. So necessarily, we have to use the approximation to the normal distribution. Also, here we can apply the correction of continuity. Being less or equal to 25 means less or equal to 25.5. So we add 0.5 here as a correction of continuity because we're saying that this discrete distribution is approximated by a continuous distribution. Okay. Well, the rule of the approximation is also included in the math tables. This was explained in a video of the formula of the normal distribution. So the average is 40 and the variance is 40. Okay. and then we standardize. We subtract the mean, we divide by the standard deviation, and then we look this value into the standard normal table, and finally we have the solution. Okay, and so here I finished this video about errors in hypothesis tests.